In the previous video, we have differentiated between exact differentials and inexact differentials. Here, we will differentiate the functions into two categories, namely the state functions and path functions. As the name suggests, there are certain functions that we come across in thermodynamics which depends only on the initial and final states. For example, you consider functions like pressure. Suppose the initial pressure of a system is P1 and the final pressure of a system is P2. Then you will be able to write the change in pressure delta P is simply equal to P2 minus P1. When you write delta P equal to P2 minus P1, you are least bothered about how the system has changed its pressure from P1 to P2. We consider only the initial value of the pressure and the final value of the pressure of the system. Means we do not give importance to followed by the system in reaching from initial pressure to the final pressure. Hence, the infinitesimal change in pressure of the system I can write as dP. dP denotes the infinitesimal change in the pressure. So dP will be equal to P2 minus P1. P2 minus P1, where this P2 and P1 are closely, very close to each other, or they are separated only infinitesimally. Now, dP is representing a very small change in pressure. In the same manner, you consider quantity like volume. So, if V is the volume, then I can write the infinitesimal change in volume by dV. Infinitesimal change in volume by dV. And this dV will be written as simply V2 minus V1, or it can be written as V final minus V initial. So it doesn't depend whether the volume has reached its final value too fast or too slow. It all depends only on the initial and final values of the volume. So both dP and dV, are known as state functions. You can see in the adjacent diagram, a PV diagram is shown and two states are shown here. One is marked as A and other is marked as B. These two are the two different states. Say A is the initial state and B is the final state of a particular system. And the state A can change to state B through a large number of paths. Say there are paths indicated as 1, 2, 3, 4, 5, 6. There can be any number of paths here. Now, if any function is a state function, then that function will have a well-defined value at the initial point A, and it will have a well-defined value at the final point B. And whatever be the path followed by the system in going from the initial state to the final state, the difference in that function will depend only on its initial and final values. Means it will be independent of the actual path followed by the system. Hence, such functions are known as state functions. So already I have introduced, there are the two very common state functions in thermodynamics. One is the pressure and the second is the volume. So I can give you some more state functions. You consider same manner temperature. So you can see that a differential change in temperature dt will be equal to T2 minus T1 or T final minus T initial. So these state functions can also be called or considered as some sort of point functions. State function can also be considered as some sort of a point function. The reason is that at every point in the PV or indicator diagram, this function will have a specified value. Okay. Now another example for state function in thermodynamics is internal energy function. We'll call internal energy, and you can see that this internal energy is actually a function. So internal energy function U is also a state function. So I can say du is equal to some U final or U2 minus U1. It means that if the system is having an internal energy at the point A, say, so I'm calling this one as Ui, and the state is said to have an internal value for internal energy at B. So this is final, suppose that. Now if somebody wants to find out the change in internal energy of the system between the initial state A and the final state B, it has got only one answer, that is du or delta U is equal to the final value of internal energy, that is U of which is at B, minus the initial value of internal energy, that is Ui which is at A. Means even though there are a large number of possible paths along which the system may move from A to B, whenever you are calculating the change in internal energy of the system, you need not consider the various possible paths. Means such functions depends only on the initial point and the final point, and these types of functions are generally known as what is known as a state function. Okay. Now what is the benefit of a state function? As you can see, a state function is a kind of exact differential. A state function can be represented as an exact differential. Already we have seen what is the advantage of an exact differential. An exact differential can be readily integrated. It's a perfect differential. So a state function can be represented by an exact differential. That is the mathematical advantage of such functions. That is, hope you remember, when do you call a function z as an exact differential? That is functions like pressure. Suppose you are considering the closed integral of pressure, means over a cycle, that will be equal to 0. Similarly, closed integral over volume also will be equal to 0. Or I can say that is a case of closed integral dt equal to closed integral du. All these are equal to 0. So such functions are what are known as point functions. Now the conclusion is that all state functions are exact differentials, or they are perfect differentials. So they can be integrated to give the final value minus the initial value. Okay. Now let us regard other type of function which are known as path functions. So as the name suggests, the path functions will be depending on the actual path that is followed by the system. For example, let me take examples for path functions. See, for example, there are two common examples for path functions in thermodynamics. One is heat. One is heat Q, and another one is work done, work W. Heat and work are not having the same status as that is enjoyed by quantities like pressure, volume, temperature, internal energy, etc. The reason you can clearly understand, what is the basic difference you can clearly understand. The basic difference is that suppose that I am writing dW. Let me write dW. I am writing dW. See, the system is initially at a point A. The system has finally achieved a point or a state B. Now, if I want to find out the work done, infinitesimal work done between system point A and system point B, then my question, can you write this one as work WB minus WA? You just think, will it be having any meaning if I write it like this? dW, will it be equal to WB minus WA? So when I write WB minus WA, what does it mean? It means that there is a value for work at A and there is a value for work at B. Does it make any sense? Actually, you will understand that work has got no meaning at 2 points A and B. There is no meaning for work at a point. Hope you remember when we discussed about the meaning of work earlier. Work was regarded as a process. Work is not regarded at a point. I told you there is no meaning for work or heat in a system. So heat is or work is regarded as a process. So dW will be equal to WB minus WA has got no meaning. So I cannot write dW equal to WB minus WA. So what is the meaning of dW? dW is not a small change in work. dW cannot be called a change in work. So there is no meaning in saying, this is something what is very important. Never use this one in changing work. Change in work. No meaning in saying change in work. Yes, let me go to change in work. So change in work is of no meaning. Instead, I can say change in pressure, I can say change in volume, change in temperature, change in internal energy, everything is possible. Okay. Similarly, change in heat you cannot use. That is meaningless. Change in heat is meaningless. Change in heat is also meaningless. Meaningless. You can see this one. And so it tells you that unlike pressure, volume, temperature, internal energy, etc., work and heat are not state functions. Instead, they are path functions. So I will say that these functions, which are path functions are inexact differentials. Path functions are inexact differentials. This is the way in which we will label them mathematically. Path functions are inexact differentials. And I hope you remember, inexact differentials are distinguished by writing some cross over it. I told you that d bar W we usually write. Similarly, we will be writing d bar Q. Instead of writing simply dq, in order to tell that this Q and W are not state functions, instead they are path functions, we'll write them as d bar w and d bar q respectively. So that is our conclusion. There are two kinds of functions used in thermodynamics. One set of functions are known as state functions, which are path independent, whose value depends only on the initial and final points reached by the system, and they are usually represented by exact differentials. They can be readily integrated, and hence they are actually point functions. And other type of functions are known as path functions. These path functions are inexact differentials. They are not defined at any point. They actually depend upon the actual path followed. So you cannot regard change in that function. That is meaningless. So the best example are heat and work, both of which are path functions. So in order to distinguish the path functions or inexact differentials from the state functions or exact differentials, we are usually putting a cross mark over the inexact differentials. So remember the difference between the two. Whenever we are using these quantities, especially work done and heat, when we consider their infinitesimal changes, we are supposed to use these cross symbols. Even if that symbols are not used, just understand that there is no meaning in saying change in work or change in heat. That is the thing. So one more thing you can just conclude. Since this w and q are not state functions, if you take closed integral of work over a path, that is not equal to 0. Closed integral over a path for q is also not equal to 0. So these two are the properties of inexact differentials. So you will be familiar with the use of these inexact and exact differentials and the corresponding state and path functions in our first law of thermodynamics. Thank you.